Right, so I'm just going to introduce what a permutation actually is. If we have a set, say, just the set of numbers 1, 2, 3. A permutation is essentially an order that we can put these numbers in. One permutation might be that 1 goes to 2, that 2 goes to 1, and 3 just matches itself. Okay, so essentially the order then becomes these numbers in the set 2, 1, 3. Okay, but we want a more compact way to write this, and what we do is we will write this permutation here. We use cycle notation, so we write 1, 2, and then we can just leave the 3, or we could write 3 in a little bracket as well. And this just means what you do is when you want to know where a number goes, you find that number, and then it goes to the number immediately to the right of it. So 1 goes to 2. Now, where does 2 go? 2 goes, well, we get to the end, so we go back to the start, goes to 1. Where does 3 go? Well, 3 just goes to itself. Okay. So we can make a set of the possible permutations on the set of numbers 1, 2, 3. And this set would be the one where all the numbers map to themselves. There's the permutation we just mentioned. There's one where 1 goes to 3, and we're just going through these systematically, where 2 just goes to 3 and 1 stays by itself. Then there's where 1 goes to 2, 2 goes to 3, and there's 3 goes to 1 obviously, and there's 1 goes to 3, goes to 2. Okay. Note that you can write these differently as well, and the permutation 2, 3, 1 is equal to 1, 2, 3. Okay, because if you look at 1, it goes to 2 here, 1 goes to 2 here, 2 goes to 3, 2 goes to 3, 3 goes to 1, 3 goes to 1. Okay, so they're equivalent notations. Then we can introduce an operation, a binary operation, and we call that composition. And what composition of the elements does, so let's take the example of 1, 2, and we're going to compose that with 1, 3, 2. Basically, we start on this right hand side and we see where the elements go, and whichever element we get in here, we look at where that goes in the second one. We can also write this a bit more compactly. It's just 1, 2, 1, 3, 2, and the composition is sort of implied. So looking at this, 1 goes to 3, and then 3 goes to nothing. And it's important we always start on the right. So 1 just goes to 3, and then, so now we've got 3 here. We want to look where 3 goes. 3 goes to 2, 2 goes to 1. So 3 goes to 1. And there we go, and then 2 goes to 1, 1 goes to 2, so 2 maps to itself. All checks out. Now, I want to convince you that this group, and I've called it S3, know that the set of all the possible permutations with the numbers 1, 2, 3, 4 is called set 4, and the set of all possible permutations with the numbers 1 up to n we just call Sn, okay? That's notation. And I want to convince you that S3 is a group. It's pretty obvious that any composition keeps us within the group. How can you get to a permutation not involving the numbers 1, 2, and 3? The numbers 1, 2, and 3 doesn't make sense. You can't map like 3 to 4 in this set, so it is closed. That's one of the what we're going to look for is an identity element and a inverse element. So 2, 3, compose with 1, 2, 3. Well, 1 goes to itself. Alright, 2 goes to itself, 2 goes to 3, and 3 goes to itself, 3 goes to 2. So we close that. And then that's clearly equal to 1, 2, 3, 2, 3. We'll just check this because 2 goes to 3, 3 goes to itself, so 2 goes to 3. And then the 3 goes to 2, 2 maps to itself, so 3 is going to 2, and then 1 just maps to itself. Okay, clearly 2, 3 is the identity. So if we're looking to find a way of finding inverses, which means that the inverse of x of an element x is that the element that multiplies with x on both sides to give the identity. Let's take the example of 1, 3, 2, and we want to find the inverse of this. And intuitively, we just swap the order of these. So instead of 1, 3, 2, we do 2, 3, 1. Why does this work? Well, because this will take us this way, and then the inverse, then because we swap the order, just takes us back again to where we started. Right, so every element should map to itself. So let's just check that for this example. 1, 3, 2, and we'll just multiply by from one side, but you should check to really check identity, you should multiply from the other side too. 2 goes to 3, 3 goes to 2, so 2 maps to itself. 3 goes to 1, 1 goes to 3, so 3 maps to itself, and 1 goes to 3, and 1 goes to 2, 2 goes to 1, so 1 maps to itself. Alright, so we haven't shown associativity either, but again, we haven't proven that Sn are groups. Sn is a group for all natural numbers, and of course n is the natural number of this set isn't very well defined if it's not. So yeah, I just wanted to do this as an example of a group that's not the integers or something you might have worked with before. Other types of groups can involve matrices and the like, and we'll see more of that in the future. But when we're looking at more specific theory to do with groups, we're not going to consider each of these examples in their own independent video, but they'll all pop up at different points in time. If you do have any questions about this, let me know down in the comments. I'll try to clear up any queries. But for now, that is it, and I hope to see you